The concept and the ideas behind an electric dipole are not very challenging. It's just a matter of going through and understanding some definitions and what's going to happen. So as you can read here, an electric dipole is where you have two equal and opposite charges that are somehow connected in some way, producing a single entity, but I have opposite ends. So I've got a negative end here and a positive end here. So in my picture, I've labeled each charge with a value of Q, and the distance between them is I'm using just the letter D. So this definition here of a dipole moment is a lowercase letter p with a little vector arrow across the top. That does look a lot like momentum, but we don't use momentum and dipole moments together, so it shouldn't be a problem. And so the dipole moment is simply the amount of charge multiplied by the distance apart. So that is a definition that is just a definition that we will memorize for the most part. Again, as I've mentioned, there's not typically a lot of electric dipoles on an AP physics exam. Not that I can recall in recent memory at all. So if it is, it's going to be a multiple choice kind of a question. And looking at the equation sheet, this is not going to be on your given equation sheet. We have a direction for the dipole moment. It's just a definition that we made forever ago. And by we, I mean obviously humans. Points from negative to positive. So don't allow this to confuse you about an electric field. An electric field points in the direction that a positive test charge would go. Well, a positive test charge wouldn't actually move in this direction. So this is a completely separate definition just for a dipole moment, pointing from negative to positive by definition. And so what we're going to do is we're going to look at this electric dipole when placed in an external electric field. So that electric field is going to push independently on each individual charge. So I have a positive on the top and a negative down here. And because an electric field pushes positives with it and it pushes negatives against it, you can see the red arrow showing the force on the positive and the force on the negative. That force can be determined by taking the charge and multiplying it by the field, so Q times E. We see that we have equal and opposite horizontal forces, so our net force is going to be 0, but we see that we're going to end up with a torque. What we have here is commonly referred to as a force couple. A force couple just means that I've got equal forces going in opposite directions, but as you can see there, different line of action. So in other words, we're not pulling aligned with our center, we are pulling somewhere off the center, producing a torque. So I have a torque caused by the positive, a torque caused by the force on the negative. I can see that both of these torque values are going to produce a clockwise rotation. So these two charges will produce a common torque. So if I scroll down and focus on just one at a time to simplify this. So obviously the distance from our pivot point is going to be the center. So if I look at from the pivot out to where our charge is, that distance R is going to be half the distance D between my two charges. So R cross F is our is our equation for torque. So R is going to be D over 2. We have our force F, which I'm going to eventually replace with an equation. We'll leave it as F for now. And then I have this cross product. Cross product says use sine if the angle is between our vectors when they are tail to tail. So the distance vector goes from our pivot out. Our force vector I could slide over here, and so there I can see that it is in fact a tail-to-tail orientation. So sine goes right there. So this right here in parentheses will be the torque caused by the force on the positive only, and I'm going to get all the same things happening for the negative. So for the negative side, I just double this. So I double it, takes away the 2. Instead of force, what I'm going to do is put in Q times E. So I have my distance, I have my force Q times E. Sine is still there. And when I come down here, I recognize that D times Q, scrolling up, D times Q all the way up here is going to be that dipole moment, letter P. So I can replace that letter P there. So P times our electric field times the sine. Sine is a cross product, so I can come down here, P crossed E is going to give us the torque on our dipole. Cross product means that we need perpendicular components. If P points from one charge to the other, and E is the field, if I scroll up, I most certainly want this to have some kind of a perpendicular component. If this thing is aligned horizontally, so if P and E are in the same direction, then I'm going to have these two forces pulling in the same line of action, and I get zero net torque. So I do have to have some perpendicular component, hence the cross product. So if we look at an electric dipole in this field, we know that any object, this is not an electric issue, any object, if we have work done against a field, we get a potential energy gain. I commonly reference gravity for this one. Gravity pulls down. The gravitational field is down. How do you gain potential energy? By moving something against that field so that the field later on can do work to bring it back. So if I allow a field to do work, we lose potential energy. Let something move down, I don't have to push it. Gravity does all of that for me, and it loses potential energy. And it turns it into most likely kinetic energy or something else. So if we look at the work done by the field, the work done is going to produce a loss in energy, hence the negative sign. So we have this equation from long ago in our rotation section, torque, which is our angular force multiplied by our angular distance, force times distance. And now we have a way to express our torque. It's P crossed with E. So we don't want to have to deal with a cross product, so we bring in a sine function instead. And so we have P E sine theta D theta. This dipole moment in this electric field, they are both constants because this is Q times D, both constants, constant electric field. So we bring these out. We are taking the we're taking the integral of sine, which is negative cosine. So this negative and the negative I'm going to get from doing an integration cancel, and I'm left with P E cosine theta. Cosine is associated with a dot product. So all of this was giving us a negative or a loss of potential energy. So when I come down here, so negative equals the negative on the right hand side here ends up canceling out. So negative U equals positive PE cosine theta. So when we come down here, just slide the negative from this side over here, slide it to right here instead. And we can figure out cosine is going to be a dot product. So the amount of energy that our dipole, our electric dipole, is going to have is going to be equal to the dot product of P dot E. And we throw that negative sign on there just so that we get a proper orientation of when do we have a high amount of energy, when do we have a low amount of energy. So the last thing here is this little diagram, this little picture right here. So I've got three identical electric dipoles all arranged in a particular way in our electric field. If I look at this first one here, forget about the math for a second. Looking at my positive is going to be pushed to the right. My negative is going to be pushed to the left. This one right here seems to be in stable equilibrium. If I displace it up a little bit, that electric field is going to push that net positive right back to where it was. And of course, we might get some kind of a oscillation of sorts as it wiggles back and forth before settling back in. But if we just ignore that, this thing is going to be pushed back to this particular equilibrium position. So this is our stable equilibrium. So this right here would mean that we have the lowest amount of potential energy because it's not going to naturally move to any other position. So if these two things are aligned, P and E are aligned, the dot product is a positive. The equation says your energy is equal to your dot product, and then throw a negative in front of that. So if I have a positive dot product and I put a negative sign in front, it means I have a negative amount of energy. And a negative energy just means it's low energy. So low energy, stable equilibrium, negative energy. negative potential energy to be specific. Take this and give it a full 180-degree spin, and this thing right here could be in equilibrium if I balance it perfectly. As soon as it's unbalanced, as soon as I offset this just by a little bit, what's going to happen? That positive is going to be pushed all the way around. Same thing for the negative. And so what we find here is that we have a very high amount of energy. We can't be any further away from stable equilibrium than where we are right now. So these two vectors, my green P and my red E, they are against each other. Dot product says we get a negative amount. So I get a negative dot product. Two negatives produce a positive value, and so I end up with the biggest possible number here. Positive being larger number line wise than a negative. So we have very, very high energy. We can still be in equilibrium. We would call this unstable, because if we displace it just a little bit from its current equilibrium state, it will rotate. And we have an infinite number of positions in between our lowest energy and our highest energy. Of course, this one right here would be a convenient one to look at. What happens if we are perfectly perpendicular? The dot product of perpendicular vectors says that your answer, your number is 0. So we have 0 energy, and keep in mind that 0 is bigger than a negative. So this right here gives us a reminder that negative is the lowest possible energy we could have when compared to a positive. That's obvious, and also when compared to a 0. So this was the electric dipole. We looked at the definition of a dipole moment and the direction. We looked at the torque that's going to be caused when an external when this dipole is in an external field. So our torque is P cross E, and our second slide shows what happens if we look at the positioning in terms of work and energy. So we are interested in energy, so we looked at the work that would be done by the field. And we end up with our energy is equal to the negative dot product of P and E. So dot product gives you energy, cross product gives you the torque. So it's still P times E for both of them. One is a cross product and one is a dot product. Memorize it, or just think about what a dot product and cross product mean in terms of torque and energy. And again, there's not going to be much on an AP exam. It might be one question. I think any question that you might see would probably be related to looking at the orientation of a dipole and maybe having to know the direction of a dipole moment. I would be truly very surprised if they expected you to actually use this equation or to actually use this equation. You don't need this equation to look at this. Let's say you shouldn't need this equation to look at this and to figure out what kind of torque you're going to get, and to know that bigger E and bigger Q and bigger distances are going to produce bigger amounts of torque. You should also be able to look at this and recognize, if you're comparing pictures side by side, which one is going to be the biggest amount of energy. So this was the electric dipole, and this video and these notes are also supplied in our Google Classroom file, so it should all be there. These notes, 2 slides worth, along with this video.